And if you hear tomorrow, yeah, cosine similarity or dot product in attention or embedding space, you won't feel intimidated. Yes, you smile because you know it's just vector interacting. Add a row vector to a column vector. Yes, kindly just observe here. 4, 5, 6. It is one among the vector A. And if I just want to add it to 10, 20 and 30. So you might think that there is no difference between this example. And one shows yes, which we have discussed already. No, actually not. If I just want to give you, see, the exact result, and first I just show you the result, then I just come again here. So if this one happens, so observed, yes, we have already a row vector. So V, which is equal to, of course, we have an array, and observe it is row vector. Okay, so yes, 4, 5, 6, and yes, this one, it is row. And kindly just observe here, dear friends, it is minus. Actually, here when on the exact direction of the vector does not change. Okay, so but the figure shows that the vector direction flips when the scalar is negative. Now you think about this. Every image you see, every sentence an LLM generates, every embedding in generative AI, at its core is just a collection of vectors. Here let me have, this is a matrix, and if I just have this matrix I and j, that is with rows and column, and I just want to do a transpose. And as this transpose, each matrix element has a row and a column index. And the transpose operation simply swaps these two indices exactly as like m, j, comma, i. That's it. And if I just specify one thing here, so here either one row or one column depending on their orientation. Okay, so for example, let me just have 6 row, okay, 6 dimensional row vector, which it has I is equal to 1 and j is equal to 1 to 6. Okay, so whereas if I just make this 6 dimensional row vector into column vector, what happens? I has 1 to 6 and j has 1. So swapping the I and j indices swaps the rows and column. That is what happened. And here, yeah. Happy morning, dear friends. Here's yours, Dr. Rajanta. Welcome to Demystify with Ajay. Dear friends, imagine you open Google Maps. You see a small blue arrow. That's you. It has a direction. It has a magnitude. How far you need to go. So that tiny arrow is not just a symbol. It's a vector. Now you think about this. Every image you see, every sentence an LLM generates, every embedding in generative AI, at its core is just a collection of vectors. Difference before neural network or before transformer or before diffusion model, there were vectors. Difference in today's session, we are not just learning maths. We are learning the language in which AI thinks. We start simple. What is a vector or how do vectors combine? What happens when we scale them? What does inner product really means geometrically? Then we shift from theory to code. So we will create a vector in NumPy, we will add them, we will scale them, and of course we will visualize the geometry too. Difference because in AI, understanding vector is like understanding alphabets before writing a poetry. And today, yes, we begin that alphabet. Difference. A vector is an ordered finite list of numbers. Vectors are usually written as vertical arrays, yeah, surrounded by squares or surrounded by curved brackets. As in like this square bracket, it is written as minus 1.1, 0.0, 3.6 or minus 7.2. They can also be written as numbers separated by commas and surrounded by parentheses. And in this notation style, yeah, the vector above written in the square bracket, yes, it is written as like this, the same thing, minus 1.1, 0, 3.6 and minus 7.2. Difference the elements or these entries or coefficients or components of a vector or the values in the array. And here the size, which is also called as like a dimension or length of the vector, is the number of elements it contains. And here the vector here in this above, for an example, has a size 4 and its third entry, it is 3.6. Yes. So the vector of size n, which we just specify as like an n vector. And if I just specify like this, dear friends, kindly just observe. So one vector which is considered to be a same number. Yes, exactly. That is what. See, actually, we don't distinguish between one vector or towards like this, a square bracket, which is, we just specify like this, 1.3, and it is as the same number 1.3. That's it. And we often uses symbols to denote these vectors, a small lowercase or an uppercase or a beta like that. And dear friends, if we denote an n vector using a symbol as like a, so the ith element of vector a is denoted as like ai, where the subscript I is an integer index that runs from 1 to n. Yes, the size of vector. Let me just take, if we just have two vectors, a and b. Okay, so a and b which are equal and which we denote it as like a equals b. If they have the same size and each of the corresponding entries is the same, then a and b are n vectors. That means ai which is equal to bi. Yeah, exactly. So ai which is equal to bi for all i's. So here if it is a1, yeah, which is equal to b1 until an which is equal to bn. Difference, the number or values of element in a vector are called scalars. So we will focus on the case that arises in most applications where the scalar are real numbers. And dear friends, if in this case we refer to a vector as real vectors, so we just denote it as like this, R. So the set of all real number is written as this capital uppercase R. And the set of all real n vectors is denoted as like n, R to the power of n. So here A belongs to R to the n is another way to say that A is an n vector with real entries. So here we use the notation as like A belongs to R to the power of n, means that A is an element of a set of Rn. Difference, it is sometimes useful to denote vectors by concatenating or stacking two or more vectors. As in like that, so kindly just observe here. Let me just have a vector A which has B, C and D. So B, C and D are also a vectors. So if B is an M vector and here C is an N vector, and let me just have D as a P vector. So this defines that M plus N plus N vectors. And how it is would be specified? Yes, kindly just observe A equals B1 to Bm. And here C, it is C1 to Cn. And lastly, this D, it is D1 to Dp. So the stacked vector A is also written as like A is equal to B, C, D. And for an example, if A is a 3 vector, so here let me just have, yes, of course, 1, A is the 4th vector. Yes, of course, A, A1, A2 and A3. Difference in this equation, we just say B, C and D are subvectors or slice of A with the size as like M, N and P respectively. And here, if we just specify this colon notation is used to denote subvectors. If A is a vector, then A R colon S is the vector of size S minus R plus 1 with the entries as like A R till A S. And how it would be specified as like a subvector? Yes, dears. A R colon S, which is equal to A R till A S. So the subscript R colon S is called the index range. Difference, a zero vector is a vector with all elements equal to 0. So sometimes the zero vector of size n is written as 0 subscript n. So where the subscript denotes the size. But usually a zero vector is just denoted as 0. That's it. The same symbol used to denote the number 0. And in this case, you have to figure out the size of zero vector from the context. Okay, as a simple example, if A is a 9 vector and we told that A is equal to 0, the 0 vector on the right hand side must be the one size of 9. So even though 0 vector of different size or different vectors, we use the same symbol 0 to denote them, because it can mean different things depend on the context. When coming towards this unit vector, dear friends, as standard, yes, the unit vector is a vector with all elements equal to 0, except one element which is equal to 1. So the ith vector, the ith unit vector is the unit vector with ith element 1 and denoted as like e to the subscript of I. So for an example, let me just have here, it is E1, it is 1, 0, 0, and E2, it is 0, 1, 0, E3, it is 0, 0, 1. So are the 3 unit vector of size 3. So the notation for unit vector is an example of the ambiguity in notation noted here. And here EI, e to the subscript I, denotes the ith unit vector and not the ith element of a vector E. And here for ones vector, dear friends, we use the notation 1 for ones vector, for the n vector with all its element equal to 1. And we also write 1 if the size of the vector can be determined from the context. Dear friends, let me just take a 2 vector can be used to represent a position or a location in a 2-dimensional. Okay, 2-dimensional space. That is a plane. As like shown here, kindly just observe the 2 vector x specifies the position. Okay, and here it just shows that x, it is what the dot with coordinate x1 and x2 in a plane. And here the 2 vector x represents a displacement in the plane. Yeah, by x1 in the first axis and x2 in the second axis. And dear friends, if we just specify this in a 3 vector, if it is used to represent a location or position of the some point in 3-dimensional, that is 3-dimensional space, the entries of the vector give the coordinate of a position or location. And here a vector can be used to represent a displacement in a plane or a 3D space. So in which case it is typically drawn as like an arrow. So a vector can be used to represent the velocity or acceleration at a given time of a point that moves in 3D. And here a color. So dear friends, a 3 vector can represent a color, which it gives the red, green and blue. So intensity value often between 0 to 1. And here if I just specify vector of 0, 0, 0 represents the black, and if I just specify vector 0, 1 and 0 represents a bright pure green color. And even if you just specify something values as like 1, comma 0.5, comma 0.5, of course, it represents a shade of pink. And when coming towards those quantities, yes, dear friends, an n vector q can represent the amount of quantities of n different resources or products held by an entity. So negative entries mean an amount of resources owed to another party. So for an example, let me just have here a bill of material. Yes, a bill of material is a vector that gives the amount of n resource required to create a product or carry out a task. And when coming towards this portfolio, dear friends, n vector, yes, can represent a stock portfolio or investment in a different asset. So with, let me just have with SI, giving the number of share of asset this I held. So the vector, let me just have 100, 50, 20 represents, yeah, that's exact the portfolio consisting of 100 shares of asset 1, 50 shares of asset 2 and 20 shares of asset 3. So short position, that is share that you owe another party, as represented by, yes, of course, you can also have a negative entries in the portfolio vector. So the entry of a portfolio vector can also be given in dollar values or a fraction of the total dollar amount invested. And dear friends, when coming towards a cash flow, yes, a cash flow into and out of an entity can be represented by a vector with positive entries representing payment to the entity. And negative entries representing payment by the entity. See, for an example, if with giving cash flow each quarter, let me just have a vector of us like 1000, comma minus 10, comma minus 10, comma minus 10, comma minus 1010. This represent a 1 year loan of $1,000 with 1% interest only payment made each quarter, and the principal and last interest payment at the last. Yes, you can also have it as like a cash flow. And dear friends, when we just take it into an audio sound signal can be represented as a vector whose entries give the value of acoustic pressure at equal spaced time. Typically, we can just take it as like 48,000 or 44,100 per second. A vector might give the hourly rainfall as like or a temperature or barometric pressure at some location over some time period. So when a vector represents a time series, it is naturally to plot X. That is versus I with lines connecting consecutive time series values. And dear friends, in many applications, a vector collects together and different quantities that pertain to a single thing or object. Yes, the quantities can be measurement or quantities that can be measured or derived from the object. Such a vector is sometimes called a feature vector, and its entities are called the features or attributes. And an n vector P can be used to record a particular customer's purchase from some business over some period of time. So if we just have, yes, xith, the quantity of item I the customer has purchased, and here this for I, that would be 1 to n. Unless n is small, we would expect many of these entries to be 0, meaning that the customer has not purchased those items. So in one variation, if we just specify PI, that represents the total dollar value of item I the customer has purchased. Dear friends, a vector of length n can represent the number of times each word in a dictionary of n word appears in a document, which we just say a word count. So for an example, if I just specify 25, 2, 0, yeah, it means that the first dictionary word appears 25 times, the second one twice, and the third one not at all. Difference: typically dictionaries are used for document word counts that have many more than 3 elements. Here, a variation is to have the entries of vector give the histogram of word frequency in the document. So for an example, if I just specify x to the subscript of 5, 0.003, it means that 0.3% of all the word in the document or the fifth word in the dictionary. So it is common practice to count variation of a word. For an example, say some same word stem with a different ending. Yes, for an example, if I just specified rain or rains, of course raining and rained might all count as rain, reducing each word to its stem, which is called the stemming. So it is also common practice to exclude words that are too common, such as like ye or as or the, so which is referred to as like a stop word, as well as word that are extremely rare. Dear friends, of course, kindly just have a note here. So word count vector are used in computer based document analysis. Each entry of word count vector is the number of times the associated dictionary word appears in the document. And kindly just observe here, if it is, the word word, thrice it appeared. In, twice. And number, once. Horse, of course, no, none times. And the, 4 times. Document, it is twice. Difference, two vector of the same size can be added together by adding the corresponding element to form another vector of the same size, called the sum of vectors. And dear friends, vector addition is denoted by the symbol plus. So thus the symbol yes plus is overloaded to mean scalar addition when scalar appears on its left and right hand sides, and vector additions when vectors appears on its left and right hand sides. So let me just have, for an example, kindly just observe the 0, 7 and 3 is added to another vector 1, 2 and 0. So when we just add this, so 0 plus 1 it is 1, 7 plus 2 it is 9, 3 plus 0 it is 3. And here, yes, of course, vector subtraction, it is also as like a same, similar. Yes, kindly just observe, if I just write 1 and 9 of a 2 size with the 2 size, and here 1 and 1 as another vector, if I just subtract both the things, so 1 minus 1 it is 0, 9 and minus 1 it is 8. Of course, this is what the resultant. So the result vector subtraction is called the difference of two vectors. Dear friends, there are several properties of vertical additions are easily verified. So any vectors as like A or B and C of the same size. So kindly just observe here, vector addition is commutative. Yes, A plus B, which is equal to B plus A. And vector addition is associative. A plus B plus C, which is equal to A plus B plus C. So we can therefore write both as like A plus B plus C. Yes, of course. And here A plus 0, which is equal to 0 plus A, which is A. Yes, adding the 0 vector to a vector has no effect. This is an example where the size of 0 vector follows from the context. Yes, it must be the same as the size of A. And kindly just observe A minus A, which is equal to 0. Subtracting a vector from itself yields the 0 vector. So here 2, the size of 0 is the size of A. Dear friends, to show these properties hold, we argue using the definition of vector addition and vector equality. As an example, okay, let us show that for any n vector A and B, we have A plus B which is equal to B plus A. Yes, this ith entry of A plus B is by definition of a vector. How we just write? Yes, A ith plus B ith. So the ith entry of B plus A which is equal to B ith plus A ith. So for any two numbers, we have AI plus BI which is equal to BI plus AI. So the ith entries of vector A plus B and B plus A are same. So this is true for all the entries. So by addition of vector equality, we have A plus B which is equal to B plus A. So verifying identity like the ones and many other we will encounter later. Yes, can be tedious, but it is important to understand that the various property we will list can be derived using elementary arguments like this, okay, like one among this which we just specified as like a commutative. And when vector A and B represent displacement. Here, dear friends, the sum of A plus B, yes, is the net displacement found by first displacing by A, then displacing by B. And kindly just observe here, so this lower blue color arrow shows the displacement of A. And the displacement of B, yes, of course, this is also. So, as the shorter blue arrow here. So starts from the head of displacement of A and ends at the sum of displacement of A plus B, which it just shows in a red arrow. And of course, here this is what the displacement of A plus B, and if I just want to show what is the displacement of B plus A, yes, the same like this. Here it would be like this. So this is A and here it would be B and this is B plus A. So this is how it happens. And dear friends, the displacement between 2 points. Yes, if the vector, if we just specify the vector P and Q represents the position of 2 points, whether it is in 2D or 3D, then P minus Q is the displacement vector from Q to P. So that is what? From Q to P. We have to specify in that direction. Dear friends, another operation is scalar multiplication, or we can just say scalar vector multiplication, in which a vector is multiplied by a scalar, yes, a number, which is done by multiplying every element of the vector by that scalar. So scalar multiplication is denoted by just as like a position, okay, of a vector by the thing. And here we can just say, typically we can just say a scalar on here as like a left position. So kindly just see here, minus 2 is a scalar and 1, 9, 6 are the vector. If we just multiple both the thing, yes, minus 2 product to 1, yes, it is minus 2. And minus 2 multiplied by 9, it is minus 18. And minus 2 multiplied by 6, it is minus 12. Dear friends, scalar vector multiplication can also be written with the scalar on the right. Yes, you can also have like this 1, 9, 6. This is what the vector, and here 1.5 as a scalar value. Yes, what would be the resultant? Yes, 1.5 and 13.5, and here it is 9. Yes, so the meaning is the same. It is the vector obtained by the multiplying each element by the scalar. And here a similar notation is A by 2, where A is the vector, meaning 1 by 2 of A. So the scalar vector product, here it is minus 1 of A, is written simply as like minus A. So note, 0A which is equal to 0. Yes, where the left hand 0 is the scalar 0 and the right hand 0 is the vector 0 of the same size as A. Dear friends, let me just have some properties. See, by definition, we have, okay, the first one, yes, we have alpha A which is equal to A alpha. For any scalar alpha, and any vector A. So this is what specified as like a commutative property of a scalar vector multiplication. It means that scalar vector multiplication can be written in either way. Yes, either way as like alpha A or which is equal to A alpha. And even sometimes scalar multiplications obeys several other laws that are easy to figure out from the definition. Yes, for an example, it satisfies the associative property. So here, if A is a vector and beta and gamma are scalar, we have beta gamma into A, which is equal to beta into gamma A. On the left hand side, we see this scalar multiplication. And yes, of course, kindly just observe this is a scalar vector multiplication on the right hand side. Yes, we see two scalar vector product. As a consequence, we can write the vector above as like beta gamma A. Yes, it denotes not matter whether we interpret this as beta gamma into A or beta into gamma A. And here the associative property holds also when we denote scalar vector multiplication with the scalar on the right. See, for an example, we have this one beta gamma A which is equal to beta A gamma. Yes, here kindly just observe which I just say beta gamma A which is equal to beta A and gamma. Of course, this can also be written. And consequently, we can write both as like beta A gamma as a convention. However, this vector is normally written as yes, beta A gamma or beta gamma A. If A is a vector and beta gamma are scalar, here kindly just observe beta plus gamma into A, which is equal to beta A plus gamma A. And this is the left distributive property of scalar vector multiplication. Different scalar vector multiplication like ordinary multiplication has higher precedence in equation than vector addition. So the right hand side here beta A plus gamma A means yes, this is one vector and this is another vector. Yes, it is useful to identify the symbols appearing in the formula. So here the plus symbol in the left side is yes, addition of scalar, and where the plus symbol of here in right side denotes vector addition. When scalar multiplication is written with the scalar on the right, we have the right distribution property. And dear friends, you can also have here I just specified beta into A plus B, which is equal to beta A plus beta B. Yes, can also one more property I just write. Kindly just see here A beta plus gamma, which is equal to A beta plus A gamma. Yes, scalar vector multiplication also satisfy here. Okay, let me just take this right distributive property. So here beta into A plus B, which is equal to beta A plus beta B. So for here any scalar of beta and any n vector of A and B. So in this equation, both of the symbols refers to the addition of vectors only. Yes, here this is also a vector addition, this plus symbol, and here this plus symbol also specify addition of n vectors. And dear friends, here I just want to specify one thing, yes, linear combination. Dear friends, here if for a vector A, if I just have AI till AM or vectors and beta 1 till beta m are scalar, then the n vector which is equal to beta 1 A1, beta 2 A2 till beta m AM. So is called the linear combination of the vector a1 till an and the scalar, yes, beta 1 to beta m are called the coefficient of this linear combination. And dear friends, if we have a linear combination of unit vectors, yes, we can write any n vector here b as a linear combination of standard unit as like b1 e1 till bn en. And here in this equation, bi is the ith entry of b, that is a scalar. And here ei is the ith entry of unit vector. And here towards the displacement, yes dear friends, when the vector represents a displacement, a linear combination is the sum of scaled displacement. And here kindly just observe, we have two vectors a1 and a2. Yes, it is denoted with a arrow symbol. And here the linear combination of this. So here this linear combination is the sum of scaled displacement. So if we just specify like this, so here it is 0.75 a1 and here 1.5 a2. So when we just made here towards the summation of b, which is equal to 0.75 a1 plus 1.5 a2. And dear friends, here let me just represent this in a cash flow replication. Yes, suppose that C1 till Cm, okay, let me just have C1 till Cm are vectors that represents cash flow, such as particular types of loans or investment. So the linear combination of here is the function f, which is equal to beta 1 C1 till beta m Cm, that represents another cash flow. So we say that the cash flow f has been replicated by the linear combination of the line. So original cash flow, that is as like C1 or C2 or Cm. And here let me just have an example. So here kindly just observe C1 1 comma minus 1.1 comma 0. This represent, yes, $1 loan from period 1 to 2. Okay, from 1 to 2 with the 10% interest. And here if we just take C2, which is equal to 0, 1 minus 1.5 represent, yes, $1 loan from period 2 to period 3 with the 10% interest. So the linear combination here, it is represented as like D, which is equal to C1 plus 1.1 C2. Where here it would be, yes, represented as 2 period loan of $1 in period 1 with compound 10% of interest. And here we have the replication, 2 period loan from 2 1 period loans. So from 2 1 period loans. And next, of course, important topic, yes, inner product. Dear friends, which is also called the dot product of two n vector, which is defined as like, yes, A transpose B, which is equal to A1 B1 plus A2 B2 till AN BN. Yes, here the sum of product of corresponding entries. And specifically between an example, kindly just observe, if we have minus 1, 2, 2 as a vector t, and if we just specified a transpose of this A, and of course if we just product it, dot product with the another vector b, 1 0 minus 3, and kindly just observe, here we would be the resultant. Yes, this minus 1 into 1 plus 2 into 0 plus 2 into minus 3, and resulted with minus 7. And dear friends, here when n is equal to 1, the inner product reduces to the usual product of two numbers. And let me just have some properties. Yes, the inner product satisfies some simple properties that are easily verified from the definition. Dear friends, if we have A, B and C are the vectors of same size, and here gamma is the scalar. And here when we just go towards the commutative property as like A transpose B, which is equal to B transpose A. Yes, the order of two vector argument in the inner product doesn't matter. And when we just go towards the associative with the scalar multiplication, kindly just observe gamma A transpose B, which is equal to gamma A transpose B. So we can also write this as like gamma A transpose B. Yes, this can be. And when coming towards this distributive with vector addition, yes, A plus B whole transpose into C, which is equal to A transpose C plus B transpose C. So the inner product can be distributed across vector addition. Dear friends, these can be continued to obtain other identities also, such as like A transpose gamma B, which is equal to gamma A transpose B. Or we can also specify here as like A transpose B plus gamma C, which is equal to A transpose B plus gamma A transpose C. As another useful example, we have for any vector A, B, C and D of the same size. Here also one more. Yes, A plus B transpose into C plus D, which is equal to A transpose C plus A transpose D. And here B transpose C plus B transpose D. So this formula expresses an inner product on the left hand side as a sum of 4 inner product on the right hand side, and is analogous to expanding a product of sums in algebra. Dear friends, note that on the left hand side, the two additional symbols refers to the vector addition. Whereas on the right hand side, the three addition symbol refers here, the three addition symbols refers to scalar addition. Dear friends, a vector in Python can be represented using several data types. And here the list type may seem like the simplest way to represent a vector. And it is for some application. But many linear algebra operations won't work on Python list. So therefore, most of the time it's best to create a NumPy array. And let me just have some code snippets to create a vector. So yes, let me just provide some necessary libraries. Here I have just provided a NumPy, and of course I have included this matplotlib to visualize the plot. Okay, and yes, here I just include to avoid or ignore the warnings. And dear friends, so let me just create a vector here. Dear friends, kindly just observe here one particular thing as list 1, 2, 3, and to the same thing let me just create it with an array as 1, 2, 3. So here the variable as array is an orientless array. That is meaning it is neither a row nor a column vector, but simply a single dimensional list of numbers in NumPy. Dear friends, orientation in NumPy is given by brackets. So here it is, and the outermost brackets group all of the number together into one object. So then each additional set of the brackets indicates a row, that is a row vector, that is variable row vector. Here that is what I specified, and has all numbers in one row. And here while the column vector, okay, so has multiple rows with each row containing one number. So we can explore this orientness by examining the shape of the variables, and kindly just let I execute this and observe the output here. So here I just show you the output what we just got. So kindly just see here as list we just got 3, and to the same as array it is 3. But when coming towards row vector, Yes, the output show here is the single dimensional array. That is, as array, it is in a tuple of single size, that is the size of 3. Whereas the orientational endowed vector two-dimensional array and are stored it as in a size as like 1, 3, that is 1 row, 3 column, or 3 row, 1 single column, depending on the orientation. And dear friends, here dimensions are always listed as row and column. So kindly just have a note on towards it. Okay, now let me just discuss on operations on vector. Dear friends, so adding two vectors. To add two vectors, we can just simply add each corresponding element. Of course, we have already discussed it. So here I just show you the example. So here 4, 5, 6, it would be one among the vector, and here 10, 20, 30 be the another vector. So if we just add these two vectors, of course adding each corresponding, so 4 plus 10 it is 14, 5 plus 20 it is 25, and 6 plus 30, yes, of course it is 36. So this would be the resultant. And dear friends, as you might guess, yeah, vector addition is defined only for two vectors that have the same dimensionality. And it is not possible to add, for an example, if it is an vectors of 3, yes, of course, we can just have towards R3 as like that. Okay, and yes, dear, so if we just go for a subtraction, yes, the same thing happens. The same what we have just done in the additional. Yes, so kindly just observe 4, 5, 6 is a vector A, and if I just want to subtract it with 10, 20 and 30, so what would be the resultant? 4 minus 10, yes, it is minus 6. And here 5 minus 20, it is minus 15, and 6 minus 30, yes, of course it is 24. Okay, with the same, let me just have a resultant, or let me just have an example in Python. So kindly just observe V here, it is a vector with the element of 1 and 2. And W here we have the vector as 4 and minus 6. Yeah, when we just add the two vector V plus W, yes, kindly just observe what would be the resultant. Yes, here V it is 1, 2, and W it is 4 and minus 6. So 1 plus 4 it is 5, and 2 minus 6 it is minus 4. And to the same here we have the subtracting vectors also. So the same V and W, if we just minus it, subtract it, so kindly just observe what would be the resultant. And here it is, yes, 1, 2, 4 and minus 6 are the vectors, and here 1 minus 4 it is minus 3, and 2 minus 6 it is 8. That is 2 minus of minus 6, it's 8. Dear friends, here I just want to ask you one thing. So if we have, for an example, let I just give, can you add a row vector to a column vector? Yes, kindly just observe here. 4, 5, 6, it is one among the vector A. And if I just want to add it to 10, 20 and 30. So you might think that there is no difference between this example. And one shows, yes, which we have discussed already. No, actually not. If I just want to give you, see, the exact result. And first I just show you the result, then I just come again here. So if this one happens, so observed, yes, we have already a row vector. So V, which is equal to, of course, we have an array, and observe it is row vector. Okay, so yes, 4, 5, 6, and yes, this one, it is row. And when coming towards W, so kindly just observe here, np dot array. It is 10, 20, 30. And actually it is a row. If I just specify as transpose, yes, it is column. Yeah, dear friends, of course, you all know when we just make it a transport, of course, it is converting row into column, it is transport. Okay, so if I just specify, okay, v plus w, kindly just observe. Yeah. So the result may seem confusing and inconsistent with the definition of vector addition. So here actually, dear friends, Python is implementing an operation called broadcasting. Yes, yeah, of course, we would just discuss what is the broadcasting is. But when on just specifying this, it is an operation that exists only in modern computer-based linear algebra. This is not a procedure you would find in traditional linear algebra. Okay, so broadcasting essentially means to repeat an operation multiple times between one vector and each element of another vector. So here if I just consider, so kindly just observe, happens as like this added towards this one. Okay, and this added towards this one, added towards this one. So here how it would be, yes, of course, 10 plus 4 it is 14, and here 20 plus 10 plus 5 it is 15, and here 10 plus 6 it is 16. This is first one. And this second row, yes, it is 20. So 20 plus 4, it is 24. And 20 plus 5, it is 25. And 20 plus 6, it is 26. And last one, it is all about 30. Yes, 30 plus 4, it is 34. And 35 and 36. Dear friends, each and everything are single row. Okay, these are single row. And of course, this is an array. And of course, it is in a matrix format also. Okay, so this is what's said to be broadcasting. Okay, so let me just move on towards a vector scalar multiplication. Dear friends, a scalar in linear algebra is a number on its own, not embedded in a vector or matrix. So scalars are typically indicated using a lowercase. Okay, so here if we just specify vector scalar multiplication is very simple. Yes, multiple each vector element by the scalar. So here observe, S is a scalar. I have just written minus 1 by 2. And here B is the exact vector with an element 3 and 4. Okay, so in such a case, if I just specify to have, kindly just observe this one, it is vector scalar multiplication. So B into S, kindly just observe, it is when on multiplying 1 by 2, that is minus 1 by 2 with 3, we just get minus 1.5. And to the same, yes, minus 1 by 2 into 4, we just get minus 2. Okay. And one more thing I just want to specify, yes, kindly just observe here. Yes, here we have just printed as B into S. So one among the property, even if we just specify S into B, we would just get the same. Okay, so this is what one among the property we just seen in vector scalar multiplication. So alpha A into A alpha, that is what here. Okay, now let me just go on for scalar vector addition. So here adding a scalar to a vector is not formally defined in algebra, linear algebra. They are two separate kind of mathematical objects and cannot be combined. But however, numerical processing programs like Python will allow adding scalar to vector. And the operation is comparable to scalar vector multiplication. Yes, the scalar is added to each vector element. Added to each vector element, the same thing. So V, here we have the vector. So let I just have the vector. Yes, it is 4, 5 and 6. And when we just add to this scalar, each and every element, 4 plus 3.5, 5 plus 3.5, 6 plus 3.5. That is how it comes. Okay. And here let me just have a visualization of different scalars. So kindly just observe. Here I just want to specify the exact scalar value. So let me have these or the exact scalar value. Dear friends, let me have the scalar value, one it is greater than 1 or between 0 and 1 or exactly 0 or negative, like that. So let me just have different scalar value, and kindly just observe the first value it is 1, and second value it is 2, and third value 1 by 3, so it is 0.3, and next it is 0, of course it is 0, and last one it is minus 2 by 3, so which it just seems a negative, so minus it is 0.67. Okay, so that is what the exact value. So we have a different scalar value, and we are just going to have a base vector of 0.75 and 1. So what here it just shows, dear friends, when on just applying this, okay, so we have an let me just have a visualization of this. So the same scalar, and it is multiplied by a vector, and here we have a list of scalar, and on visualizing, kindly just observe here. So here it shows the exact visualization. So here the scalar which is equal to 1. So kindly just observe the exact distance. Okay, so here the scalar scale vector without changing their direction. So this comes from the geometric interpretation. Yes, dear. So, and here kindly just observe the exact direction and towards the vector and towards scalar. Kindly just observe here both are the same direction, and here a scalar is twice, and when coming towards 0.3, yes, it is in a positive, and both are here the scalar it is 0. And kindly just observe here, dear friends, it is minus. Actually here when on the exact direction of the vector does not change. Okay, so but the figure shows that the vector direction flips when the scalar is negative. Okay, so actually that might seem a contradiction, but there is an interpretation of vector as pointing along an infinitely long line that passes through the horizon and goes to infinity in both the direction. Okay, so yes, in that sense, the rotated vector still points along the same infinite line, and thus the negative scalar does not change the direction. So here it is contradiction. Okay, and kindly, dear friends, this interpretation is important for matrix spaces, eigenvectors, and singular vectors. All of these which are introduced in later coming sessions. Okay, and yes, I just want to show you one among the example in dot product, which is one among property, a distributive property. So kindly just to see here, dear friends, we have three different vectors. Yes, v as 0, 1, 2, and vector w, it is 3, 5, 8. And the vector u, it has 13, 21, and 34. Dear friends, here what that distributive is specified as, like, yes, if I want to make a dot product of v into w plus u, okay, which is equal to this two scalar and vector, and of course here we can just have this scalar and towards vector. So that is what we have just seen in the scalar vector distributive property. And yes, it is also going to be the same, vw plus vu. That is what here I am just going to show it in a Python. So yes, so you can also make it in a two-way computation. So one is v, the vector 0, 1, and 2, and w, the vector as 3, 5, 8, and lastly the vector u, it is 13, 21, and 34. So when I just want to add this and I want to make a dot product with this v, so that is what the exact resultant here it is. Okay, and the second one, kindly just observe here, it is VW and VU. So here what I'm just going to do is let I dot product this VW and I dot product this V and U, and then add the resultant. Okay, and what would be the exact surprising? Of course, both are equal. So that is what the distributive product in dot product. So kindly just observe, here we go. So yes, dear sir. So we just get the exact resultant as 110, and here also the same 110. And one thing I just want to specify among the transpose, yes, we have already discussed about the transpose operation, as it converts column vectors into row vectors, and of course the vice versa, row vectors into column vectors. But let me provide a slightly more formal definition that will generalize to transposing matrix. Yes. Here we have a row and a matrix that has rows and a column. So here let I have a instead of matrix, first of all, let I just take a vector. So here kindly just observe, this is a row vector, and observe what it has. So this is what, and as it is a row vector, I'm just showing it in a row 1, 2, 3. And how it is defined, it is, yes, it is a square bracket inside a square bracket. Okay, so yes, and when on just making that, so let I just first print the exact vector, and let me print the transpose of the row vector, which it just gives us an in a column wise. And when we do double transpose, dear friends, actually here it is an important rule is that transposing twice returns the vector to its original orientation. Okay, so here that is what the thing. So for an example, one thing observed here. So when I just make this transpose, first of all, here let me have, this is a matrix, and if I just have this matrix I and j, that is with rows and column, and I just want to do a transpose. And as this transpose, each matrix element has a row and a column index, and the transpose operation simply swaps these two indices exactly as like m, j, I. That's it. And if I just specify one thing here, so here either one row or one column depending on it, on their orientation. Okay, so for example, let me just have 6 row, okay, 6-dimensional row vector, which it has I is equal to 1 and j is equal to 1 to 6. Okay, so whereas if I just make this 6-dimensional row vector into column vector, what happens? I has 1 to 6 and j has 1. So swapping the I and j indices swaps the rows and column. That is what happened. And here, yeah, so this double transpose, that seems obvious and trivial, but it is the keystone of several important proofs in data science and machine learning, including creating symmetric covariance matrix as the data matrix times its transpose. So, which in turn is the reaction why the principal components analysis is an orthogonal rotation of the data space. Don't worry, we would just discuss it in later. Okay, so let I just show here. So here it is what the R, that is the same vector, and here first of all let I transfer it and double transpose. Okay, so first of all, yes. So this row vector is transposed to column vector, and on making double transpose, yes. So here we just get the output. And dear friends, so this one, if I just make with an orientation-less array, so there also you can just experience the same. So observe here, this is what my vector L. So let me have the view. So this is what the vector, and yes, as the same, let me print the vector and orientation array. Okay, so here let me just print the array and transpose of the same and double transpose of the same. So observe here, this is what the exact output. And here it's, dear friends, yeah, today we did something very important. We did not jump into deep learning directly. We do not touch neural network itself. Instead, we built the mathematical intuition that powers all of them. So now you know or you understand a vector is more than numbers. It represents direction and magnitude. And here vector addition is geometric movement, And scalar multiplication or stretches or shrinks information. Difference inner product measures similarity, the backbone of embedding and attention mechanism. And in NumPy, these ideas become real computable operations. And if you hear tomorrow, yeah, cosine similarity or dot product in attention or embedding space, you won't feel intimidated. Yes, you smile because you know it's just vector interacting. So this is how mastery begins. Small concept, deep clarity, and strong foundation. And dear friends, remember, artificial intelligence is not magic. It is mathematics made programmable. So let's continue building this foundation. Until next time, happy learning, dear friends.